So the last topic in the renal system that we're going to talk about is the control of extracellular fluid osmolarity, which is also the way we control plasma osmolarity, and something else that we refer to as water balance. So extracellular fluid osmolarity or plasma osmolarity has to do with the ratio of water to solutes in the plasma. Okay? And so this is regulated by maintaining overall water balance in the body. And we want to maintain plasma osmolarity because it's going to affect cell volume, right? If plasma becomes hypertonic, it can cause water to move out of cells and cell shrinking. If plasma becomes hypotonic, it can cause water to move into cells and cause cell swelling. So we have to tightly contain plasma osmolarity or maintain plasma osmolarity in order to ensure that the cells are functioning optimally, right? And they're not getting injured through any extreme of expansion or retraction of volume. So we maintain the osmolarity of plasma by maintaining water balance, meaning that assuming the body has a certain number of solutes, we want to maintain the water content at a fixed ratio with the solute content in order to maintain the overall osmolarity at isotonic levels. So we maintain water balance by, similar to sodium balance, by balancing the sources of water gain with the sources of water loss. Okay? So by maintaining inequality between the gains and losses, we keep our overall pool of water at the same level. So body water is gained in two ways. We either gain water through the water we consume through by itself or in the food we eat, or we gain water through water liberated from metabolic processes. Okay. Two sources of water gain. And we lose water through three primary routes. It's actually the same route that we lose sodium. We lose water through urine, we lose it through feces, we lose it through sweat. Normally, urine is the primary way that we lose water. However, of course, if you're in some sort of diarrheal state or you have profuse sweating, that can start to become a significant source of water loss. Okay? But under normal circumstances, the main way that we gain water is by consuming it, and the main way that we lose water is through urinary loss. Okay? And so based on what kind of water balance we're in, we can either have our gains equaling our losses and we're perfectly hydrated. We could have our gains outpacing our losses and we can be overhydrated, or our losses outpacing our gains and be dehydrated. So there is two main elements to controlling total body water and therefore osmolarity. We control the excretion of water by the kidneys, which is also called diuresis, right? The elimination of water through urine. And we control the thirst mechanism, which controls the oral intake of water. And so this is a negative feedback loop, and the sensors start actually at the level of the brain. Okay? And the sensors involved in maintaining water balance actually measure plasma osmolarity in a constant way. So there is a part of our brain, remember we talked about these circumventricular organs when we talked about the nervous system. These circumventricular organs, they're portions of the brain that are sitting near the ventricles, and they are capable of sensing the composition of plasma. They have a blood-brain barrier that's just a little bit more leaky, and so they sense the composition of plasma. And there's two of these circumventricular organs, one called the SFO, the other called the OVLT. And these two circumventricular organs are what we call our central osmoreceptors. Okay? Our central osmoreceptors. Central because they're in the central nervous system, osmoreceptors because they are sensitive to changes in plasma osmolarity. Okay? Now notice the position of these osmoreceptors with respect to the hypothalamus and the posterior pituitary. Okay? Remember, the hypothalamus is the part of the brain that produces vasopressin or ADH, and that hormone is released at the pituitary gland. So the main thing that controls the release of ADH, the primary control of the release of ADH, is a change in plasma osmolarity, okay, which is going to be sensed by our SFO and our OVLT. So let's say the SFO and the OVLT sense an elevation in plasma osmolarity, okay, which means that the plasma is becoming too concentrated. It has lost water and it's becoming too concentrated. Under those circumstances, the SFO and the OVLT will stimulate the hypothalamus to release ADH from the posterior pituitary. Okay. Plasma osmolarity rises, SFO and the OVLT sense that rise, and they stimulate the hypothalamus to release ADH from the posterior pituitary. Okay. Now, we know that ADH is going to bring about enhanced water reabsorption at the level of the kidneys. Right? It enhances water reabsorption at the distal tubule and the collecting duct. So that will enhance water conservation and hopefully bring our plasma osmolarity back down to normal. Okay? So the sensitivity of this ADH system is very sensitive. Okay? In a healthy individual, normal plasma osmolarity is about 290. Okay? It's about 290. The threshold for ADH release, this acronym AVP just stands for arginine vasopressin. This is another normal abbreviation for this hormone. Okay? So the threshold for ADH release is slightly lower than normal. It's actually 280. And when I say it's the threshold for ADH release, it means that plasma osmolarity has to be at least 280 in order to get any amount of ADH release. If plasma osmolarity becomes more dilute than 280, if it becomes less than 280, we essentially shut down ADH release, which means that we're not going to reabsorb water at the distal tubule and the collecting duct. We're going to produce very dilute urine in order to get rid of this extra water. Okay? Any increase in plasma osmolarity, right, as little as 1%, produces an increase in ADH. Okay? So you have to have an osmolarity of at least 280 to release ADH, and then any increase beyond that produces more ADH. Okay? So if we look at this slide, we have the SFO and the OVLT. They are the central osmoreceptors. They are sensing a change in plasma osmolarity. And if need be, they stimulate the hypothalamus, which is, in this slide, the PVN and the SON are the portions of the hypothalamus that control ADH release. Okay. So the SFO and the OVLT, if they sense a rise in plasma osmolarity, they'll stimulate the PVN and the SON to release vasopressin or ADH from the posterior pituitary. And vasopressin will act on the kidneys to increase water reabsorption. The SFO and the OVLT, when they register a rise in plasma osmolarity, they also stimulate thirst. Okay? So they also stimulate the conscious sensation of thirst to enhance water intake. So rise in plasma osmolarity causes stimulation of thirst and increased water reabsorption. Now, if you recall in the last chapter, I talked about how both angiotensin II and an increase in sympathetic activity leads to both thirst and the release of vasopressin. Okay. And so this is where the system that controls plasma volume interacts or intersects with the system that controls plasma osmolarity. Okay. Now, I told you angiotensin II stimulates thirst and stimulates the release of vasopressin. There are angiotensin II receptors on the SFO and the OVLT. So under any level of plasma osmolarity, in the presence of angiotensin II binds to its receptor on the SFO and the OVLT and stimulates thirst and also stimulates the hypothalamic release of vasopressin. Okay, so that's where angiotensin II interacts with this system. There are angiotensin II receptors on the SFO and the OVLT. Now, where sympathetic nerve activity acts is at the level of the brain. So the part of the brain that controls the output of sympathetic activity, okay, it's in the brainstem. The part of the brain that controls this is in the brainstem, and in the brain, a message that increases sympathetic nerve activity, like a drop in pressure registered by the aortic arch and carotid baroreceptors, is going to also stimulate both thirst and the hypothalamic release of vasopressin. Okay. So this is a brain circuit. The baroreceptors inform the brain of a drop of blood pressure. The brain stimulates the downward message of an increase in sympathetic nerve activity, and simultaneously it stimulates thirst and the hypothalamic release of vasopressin. So this is where these two systems intersect. Okay. So thirst and ADH release is going to be stimulated under conditions where plasma osmolarity rises, okay, or plasma volume and blood pressure drop. Okay. And the goal is to stimulate water fluid consumption and water retention. In addition to plasma osmolarity, there are other factors that can affect ADH release. Okay. And these are not factors that are really appropriate in terms of regulating blood volume or plasma osmolarity. These are things that can actually lead to inappropriate release of ADH if taken to an extreme. So things like the rate of ADH breakdown. ADH is metabolized mostly by the liver. So under conditions where the liver function has declined, you can end up with a decrease in ADH breakdown, which is going to create an increase in plasma ADH. Okay? And like I said, if that becomes significant, that can cause inappropriate actions of ADH. Intense pain, fear, and trauma. Okay? Intense pain, fear, and trauma, they all significantly increase sympathetic activation, which is going to cause an inappropriate release of ADH. And then lastly, alcohol consumption actually decreases ADH release, okay, which ends up promoting the urinary elimination of water. And this is one of the reasons why alcohol is so dehydrating, right? Consuming alcohol dehydrates people. One reason for that is the decreased plasma ADH, which stimulates really an inappropriate loss of body water.